All right, let's start. So, any questions related to harmonic oscillator? Because today we'll be addressing different problem. We will start looking at the hydrogen atom. Okay, so that's last simple problem. And of course, since it's the last, it's not so simple. All right, but we will make 3 steps towards hydrogen atom, and it will be like a nested dough, essentially, or peeling onion, essentially. We first layer, second, and third. The simplicity of that problem is that although it has 3 variables, if we consider just 1 electron in the kind of field of nucleus, right, and all these 3 variables in the right system of coordinates, they are separable. So you can consider differential equations that are kind of describing the behavior of the total wave function with respect to any of those 3 variables separately. That's where simplicity comes from, right? So you don't need to consider all 3 variables at the same time. You can consider them one at a time, and that's why it's still considered to be solvable problem. All right, but differential equations will be somewhat difficult to solve. I will just state the solution without going into details how we can obtain them. Now, the first layer is the simplest, and I'll give you a full description with the solution, but second and third, they will be a little bit more complicated. So we will just state the solution and go forward. Now, on a previous lecture, interesting question was asked, just to finish the harmonic oscillator problem. So interesting question was, when mass goes up, right? So what happens in this case? We talked about 0-point energy, right, that it goes down. And the 0-point energy was going down because it is it's equal to sum of the kinetic and potential energies, and for the ground state, and it's omega divided by 2, which is 1/2 of square root of k divided by m, right? And if mass goes up, then this expression goes down, right? So what does this physically mean? A person who asked this question was thinking in terms of possible gravitational force, but I would like to assure you that in quantum mechanics we don't consider gravity, so it has nothing to do with gravity, this mass relation and lowering the energy. So what it has to do with is actually that the Hamiltonian of harmonic oscillator, right, has this form where we have h squared divided by 2m, right, second derivative, plus kx squared divided by 2. That's the form we started with. And as you can see, this is a kinetic energy, and this is potential energy, right? Now, this, of course, is related to, if we average with the wave function, it's kinetic energy. And if we average this with wave function, that's potential energy. Now, you can see that kinetic energy actually will go down with mass, right? Because mass is in denominator. What also you can see is that we talked about this in the beginning, why electrons do not fall on the nuclei in molecules or in atoms. It's because of that second derivative, right? So in kinetic energy in quantum mechanics related to the curvature of the wave function. And if you have a wave function which looks like this, or wave function which looks like that, so say it's psi 1 and this is psi 2, kinetic energy of which wave function will be higher? 2? 2. Why? Because the second derivative of the second function is higher than the second derivative, average second derivative of the first function. And if you kind of make it to the extreme where you have just a flat wave function, free, then the kinetic energy of the flat line is just 0, right? So the reason why electron doesn't fall in the nucleus, again, is because in order to fall on the very small nucleus, it needs to be really compact. But still, every quantum object is described by a wave function which integrates with its square to 1, right? So that means the wave function that falls on the nucleus must be really, really spiky. And the kinetic energy will go up. Now, let's think what happens when we increase mass. When we increase mass, this spikiness of or the compactness of the wave function, or curvature of the wave function, will it affect energy more or less? Mass goes the opposite way, right? So, in a sense, if we have higher mass, that means the wave function can be more compact, right? And have kind of not very high kinetic energy. Why? Because although second derivative will be high with a compact wave function, but the mass will kind of lower that contribution because mass is, we're kind of considering the situation where mass is getting bigger and bigger and bigger, right? So what does this mean in terms of harmonic oscillator is that if mass is large, that means a wave function can be really localized at the bottom. And in the limit of mass goes to infinity, that kind of zeroes the kinetic energy contribution completely, right? What this means is, from the variational perspective, a wave function that lowers the potential, because the potential is left as the only player here, right? In energy expression, the potential is the only contribution if mass goes to infinity, right? So what function would lower the potential the most? Look at the potential. Right? This is potential. What function would lower the potential the most? In a way, because for the total energy, this expression is important, right? And this is the integral of dx psi star x v of x psi of x, right? So what should be psi that this expression is the lowest? Oh, it's a very simple problem, right? Can it be this? Okay, let's just play with the, say, Gaussian form, right? So you have a wave function that looks like Gaussian. Now, where should I place that Gaussian so that this integral will be the smallest? Do you know how to calculate integrals? It's area under the plot, right? So what's the problem? No, I'm just asking, where should I center the Gaussian if you have v of x like a parabola, centered at 0, right? Where should I center the Gaussian when I integrate product of Gaussian with itself and the parabola? I would get the smallest integral. At 0. Why? Because, well, if I center, say, it here, then the area under the plot will be this, right? Area. Or it's bigger than here where the potential is the smallest value. Still no idea what I'm talking about? You guys know how to calculate integrals? Okay, so what's the problem here? I'm asking where to put the wave function so that the integral with the potential will be the lowest. Well, it's at the center because the potential is the lowest. Okay, forget about Gaussian. Gaussian is too hard for you. Let's say we do this. This is my wave function. Where should I put this rectangle so that the integral, this rectangle is the wave function? It's 0 everywhere, and from a to b, it's non-zero, it's equal to 1. Or a minus b absolute value, so that square root, so that it integrates to 1 with the square. So where should I put this square? Okay, if this is hard, let's consider a different example. Imagine there is no harmonic potential, there is just a well. And the wave function is also a rectangle. And that well is 0 or a. And the rectangle, let's say also a. So where should I put the rectangle to make the integral smaller? Inside or outside? Inside. Why? What will be the value of integral? Okay, potential is equal to a outside and is equal to 0 inside. We're considering integral potential times function, and the function is real, so it's a square of the function with the potential. So what's the value of integral if I put my wave function inside the 0, right? Good. And we cannot do better than that because, well, it's everything is positive, so you cannot do better than 0. Now, let's make it a little bit more complicated. Imagine the potential is not 0 everywhere, but rather 0 in one point, and in the rest it's parabola. Right? So where should I put my rectangle so that the integral is the lowest? Huh? In the middle. Because if I put it, say, here, and it's very thin, then roughly the integral will be like a width multiplied by the value of the potential, right? So because the potential here is bigger than potential here, then to minimize the integral, it should be put in the center, right? Good. Now let's make it more complicated. Imagine you have not rectangle but a normal function, which looks like Gaussian. Where should I put Gaussian? In the middle or somewhere else? In the middle, the same logic, right? Now imagine I can play with the width of the Gaussian. What Gaussian should I take? Wide or narrow? Narrow, because the narrower the Gaussian, the lower the integral, right? Because if I take the Gaussian, which is infinitely narrow, and put it in the center, then the integral still will be 0. If the Gaussian is broad, then these areas will contribute to the integral, it will be large, right? Now, if we talk about harmonic oscillator and lowering its energy when the mass is high, then the distribution can be made very, very compact, and it will be staying at the bottom of this parabola, right? So it becomes more and more classical in a sense. Okay? In the classical limit, what do we know about oscillations? They can be frozen, right? Why? Because the lowest energy, when you lower the temperature, will correspond for the classical object with the high mass being in the bottom and not oscillating essentially, right? So the wave function can be made very compact. And that's also clear from the energy expression. But also it's like just lowering of energy with mass. It's very simple. The second derivative part is getting smaller because of higher mass, and in order to lower the potential energy, you can go to the kind of classical limit. The wave function is very narrow, and what we have here is that the position of the object will be more and more determined, right? Because we have a narrower and narrower wave function. That means you can determine what's the position of the harmonic oscillator with a better precision, right? Because the wave function is narrow, right? Probability distribution then will be also narrow, because you multiply something narrow by something narrow, you get something narrow. And so that's about mass. The higher the mass, then the more classical we're kind of closer to the classical picture, and that's the reason why 0-point energy is going down, because we're talking about the ground state, and ground state becomes kind of narrow. Okay? Any questions? Good. All right, so now hydrogen atom. With hydrogen atom, we have 3 dimensions. We have 1 proton in the center, and then we have electron, right? Proton is positive, electron is negative, and we use Born-Oppenheimer approximation, meaning that we consider nuclei to be parameters, right? Static. That corresponds to the kind of assumption that they move on a much slower time scale. So we can freeze them for our consideration and consider just electronic problem. So now we put the system of coordinates in the center of the proton, and then we'll have 3-dimensional coordinate for the electron. Now this is, as I said, Born-Oppenheimer approximation. This problem actually can be treated exactly because it's 2-body problem. You can separate center of mass of the total system and then go to the, there will be 2 variables, like we consider the diatomic oscillator, right? So there is a translational coordinate of the center of mass, and there is an internal coordinate. So the same thing can be done here, but we are not going to go into these details. We just do the Born-Oppenheimer, and results will be pretty close if you don't consider some artifacts of Born-Oppenheimer approximation. Now we centered everything at the proton, and then there is a force, right, that binds the electron and proton together. What is that force? Say it louder. Coulombic, yes. So we have electron nuclear potential, which is 1 over r, right, with minus. Why minus? Because the Coulombic force has 2 charges, right? 1 positive, 1 negative. Product of charges is negative. And it kind of makes sense because this potential lowers the energy of the system, right? By attracting positive and negative, the energy is overall lowered, not increased. So the system is becoming more stable, right? Then you will have, a kinetic energy of electron, right? So that's the whole Hamiltonian will be kinetic energy of electrons plus electron nuclear attraction. Okay? So this is after we did Born-Oppenheimer approximation. Actually, we do not consider nuclear energy of the proton. So what is the kinetic energy here? Do you guys remember? 3-dimensional case. It's like having a particle in a 3-dimensional box. Pretty much. Right? Right. So it's minus h bar squared divided by 2m, where m is the mass of electron. And here we have Laplacian. Right? So, and what is R? By the way, I forgot to put the absolute value because the Coulombic force doesn't really depend on the direction. It depends on the distance between positive and negative charge. So what is the distance in the 3-dimensional coordinate system? Like if you know your coordinate is x1, y1, z1, and the coordinate and my coordinate is x2, y2, z2, what will be the distance between us? That's right, square root of some of the squares of the differences, right? Oh, this is very useful equation, actually, expression, because, well, since we have origin at 0, then there are no differences, we just do this. Right? So that's the distance from the origin to the point that is characterized by the radius vector r that has components x, y, z. Okay? So that's just the square root of some of the squares. Okay, so what would be the approach to solve the, I'll put electronic here, electronic. What would be the approach to solve the electronic problem? How do we solve this? So you know now variational approach, right? So that can solve anything. So as I mentioned, this part is like a particle in three-dimensional box. That part, potential energy, something else, right? So how do we solve such problems? Yeah. We can find the minimum of energy, this energy, right? And but the beginning of any variational approach would be somehow write this function as some form where we know some part of it and some part of it is just some coefficients, right? So what would be the form, appropriate form, possible form for the electronic function? Just anything. Give me something. You remember the problem that we've been solving, this one, right? So it was close to particle in the box. So what we did, we just took the particle in the box functions and built the linear combination of those functions, x, right? And then we optimize the coefficients. So the same thing can be done here. Just, well, the box is three-dimensional, right? So what do we do? Do you guys remember variational principle? Should I put more problems on the exam to remind you? So in variational principle, what you potentially can do is you can build this linear combination of C and Km and then put, say, particle in the box functions right, something like that. And then you have like the whole tensor of coefficients to optimize both n, all of them, n, k, m, they run from 1 to some big number, n. Okay? And we can formulate equations on them, but that would be complicated. So what's the complication here? Where does it come from? Does it come from this part or does it come from that part? Why can't we just use one product? Because this is this problem, this part is like a particle in the box. It's just kinetic energy, right? Why can't we use particle in the box solutions? Yeah. Non-zero potential. More than that, potential is pretty nasty, right? It cannot be written as a sum of x plus some other potential of y plus some other potential of z, right? So it cannot be written like this. If it could be written like this, then we could just solve each dimension separately, right? That would be a separable case. That would be like a particle in a box with x, y, z, 3 different dimensions. Maybe the potential of the bottom of the box would be different in 3 dimensions. But here the problem is that it's not separable. The square root of x squared plus y squared plus z squared cannot be written as a sum of functions which, well, where every dimension is separate. So that is the main problem here. So what do we do? What other approaches to differential equations do you know? All right. So what can be done is, like in calculus, you probably have seen it. We can just change the coordinate system. All right. So if problem is difficult in one coordinate system, you can change coordinate system so that the problem will be simpler, right? So if kinetic energy betrayed us in this case, right? So it just doesn't give us really a good starting point. So maybe we should take the electron nuclear potential as our best friend, right? What does it suggest to you? It depends on 1 over r, where r is the coordinate from, like, essentially the distance from the center. What coordinate system? Yeah. Radial or spherical, right? So we have a 3-dimensional case, so we need a spherical system. And in that spherical system, the potential, at least, will be very simple, right? It's 1 over 1 coordinate. It's a 1-dimensional potential. Okay? But as you can imagine, things are not that easy. That's why we will approach them in, well, what, almost 6 lectures, right? If we count every lecture by 1 hour. So you may expect that the kinetic energy will become our source of our troubles in the once we switch to this spherical coordinate system, right? And but it's less of the trouble than treating everything in Cartesian. That's why we will be doing it anyway. So the coordinate system we are talking about is spherical. It has 3 coordinates because, well, we try to describe 3-dimensional space, right? And then, so the coordinates are essentially the distance, angle from the z-axis, and it's theta, and then the angle from x-axis, phi. This is y-axis, right? So those are our 3 coordinates now, instead of previously considered Cartesian coordinates. And then x can be written as now functions of cosine phi, sine theta. Y is also r or sines, and z is r cosine theta. Okay, and so I won't put everything which I have in the notes. I just want to mention that r is in the range from 0, including 0, to infinity. Then theta is within the range of 0 pi, and phi is in the range 0 to pi. Okay. Now, what will be useful, as it turns out, is step a little bit back and consider somewhat simpler problem before attacking the 3-dimensional case. Turns out that it's easier to first do the 2-dimensional version. And just trust me on that. It's going to be useful addressing the three-dimensional case later. Okay, but we will learn a lot considering two-dimensional case. In a sense, this hydrogen problem can be considered as first just say we will consider just a slice, right? Say we cut along the sphere along the y-x plane, and then we got ourselves a circle, right? And again, to make things even simpler, we will for now consider just a particle on a circle, on a ring, right? And first we'll solve that problem. It will turn out to be immensely useful then to go and consider particle on a sphere, and then after we will solve those two, we'll go and solve actually the full problem with allowing the r to be different as well. Okay, so we will essentially put some constraints on the problem first and consider simpler problems with constraints. And then once we will be more and more proficient solving the constraint problems, we will start releasing the constraints and we will end up with solution of the total problem. That's the plan. Okay? So 2D case even simpler, because then x is r, we have only one angle, cosine phi, and y has r sine phi, and there is no z, right? Okay. So this is all good. Now let's try to slay the dragon, right? And try to express the kinetic energy of this, say, electron in a two-dimensional subspace as some operator which will depend only on r and phi. Right, so this is a 2D version of Laplacian in the polar coordinates, because these are polar coordinates and these are spherical. Okay. All right. So how do we approach the problem? This is pretty much the chain rule exercise, because of the kinetic energy is proportional. We won't consider constant in front, because, well, constant is the constant in any coordinate system, right? So it does depend on coordinates, that's why it's called constant. So the kinetic energy essentially is proportional to Laplacian. That's the operator where we have d squared dx squared plus d y squared, right? So this is the thing we need to turn into, let me write down the final expression, which you will obtain in your homework, because it's a lot of math. It's relatively straightforward. I'll show you one component of it. The second you will do at home, and summing the two components, the one I will get you in class, the x part, and doing y part at home, summing together, you will be able to get this expression. Okay, so that's the plan. So listen carefully for the x component, okay? Because like you will need to repeat it for y component at home, okay? Or maybe it's pretty obvious for you. We'll see. Okay? So, all right. Now, this is the full expression, and if r is a constant, that's for a particle on the ring, right? Then all derivatives with respect to r will be gone, because r is constant. And in that case, the expression for the kinetic energy for a particle on the ring will be proportional to 1 over r squared d phi squared. Okay? And that's the Hamiltonian, which we'll be working with. It's actually, if you look at it, it's actually very, well, it's pretty much the same as a particle in a box. There we had x coordinate, second derivative. Here we have angle coordinate. And indeed, if you confine particle to be on a ring, this is like it's in the box. It's just once it goes to the left, it appears from the right. Right? So the topology is different. Now it's a circle instead of being the kind of a interval, right? And that topology actually will play a role changing the spectrum of this Hamiltonian. We'll see some differences, but also we'll have some similarities with just a particle on a box, or in a box. Right? Now, first things first. Let's just consider how can we treat the x component. Right? So you all heard about this useful, immensely useful thing as chain rule, right? Now, with working with derivatives, what helps, like with the commutators, is to have like a trial function. So just to keep track of things. Essentially, when we are interested in transferring this into some essentially derivatives of r, derivatives of phi, and then the second derivatives, all that stuff, right? So it's easier to consider this expression, right? And then write it down in terms of derivatives of function with respect to r, phi, and other things, right? For first and second mainly derivatives. And this is, you need to differentiate function twice, right, with respect to x. Now, in order to know what this is, you need to first know what this is, right? df over dx. And here, where the chain rule comes handy, you can always write f as a function, derivatives of phi with respect to derivatives of x, right? Plus derivatives of f with respect to r, and then dr over dx, right? Of course, we cannot do anything about these guys because we don't know what f is. It's just a trial function. But these things we can calculate easily because we know that the phi is from these expressions, right? We easily can find that phi is arctangent of y divided by x, and r is square root of x squared plus y squared. All right? And of course, you all can differentiate these functions with respect to x and y. Because, well, in the y problem that you will be doing at home, you will need the derivative with respect to y. Now, let's say in my notes I have this as function g. So essentially this first derivative is a function g. And then, in order to get to the second derivative, this is essentially dg over dx. And again, using chain rule, dg over d phi over dx plus dg over dr over dx. Okay. Now in this case, this guy is already calculated, but these derivatives, they will need to be found because g, you know something about g. It's not just a random function. It already contains this expression in itself, right? Okay, now let's start with the simple things, and I will tell you that d phi over dx is equal to minus y r squared. And so that we can leave it as is, but as you can see, this is a part of g, and g later we need to differentiate with respect to phi. What does this mean? We need to transfer this expression in polar coordinates completely, and we have y here, r squared, right? So, but we know what y is, and it's just once we put y and we cancel one r, that becomes minus sine of phi divided by r, right? So that's our kind of ready-to-use expression for d phi over dx. Then later we can differentiate it with respect to phi and with respect to r as a part of g. Now the second thing we need is d phi, okay, dr over dx, right? This part. And dr over dx is, we know r in terms of x, it's x divided by r, and this is just cosine of phi, because x is r times cosine phi. In the notes, by the way, I also left the derivatives with respect to y, so that you can use in the when you will be doing the homework. Now, let's combine what we obtain in as a kind of g function, right? So what is our g function? It's minus sine phi divided by r df over d phi plus cosine of phi df dr. Okay, is that clear what I'm doing here? Right, so I'm just putting these partial derivatives, the expressions obtained, and these guys I cannot do much with them, they just stay the way they are. Now, to obtain the second derivative, these guys I already know, so I need to understand what these partial derivatives are, right? dg over d phi and dg over dr. So dg over d phi is, I need to differentiate this part, and I should not forget about this part, right? So it's a differentiation of the product. So sine goes to cosine without changing the sign, cosine phi r df over d phi plus minus sine phi over r, and then the second derivative with respect to phi, right? That's only this part. Now there will be this part that will produce also two expressions. Cosine will go to minus sine phi df over dr plus cosine phi d2f, the mixed derivative dr d phi. Okay, so this is dg over d phi. Now dg over dr is done in the same way, and okay. Okay, so we differentiate first expression is r squared plus, right, and df over d phi. Then we differentiate it again. To f dr d phi. And then the second one plus cosine of phi df dr squared. Right, because this one is easy, you don't need to differentiate this with respect to r, you just differentiate this. Alright, so we found these guys. Now we need to multiply them by this functions that we already found. And let me write down the final expression. Alright, so there is a sine times cosine of phi that gives us double angles of sine, df d phi plus sine squared phi to f over d phi squared divided by r squared plus Alright, so if you remove f, then you get the, what's the second derivative with respect to x will be in terms of second derivatives or with respect to phi and r. Okay, that's the expression, and at home you will do the y part, and when we kind of add them together, you should obtain this expression. Okay, if you do things correctly. All right, any questions? No? So it's relatively straightforward math. Okay, so let's now then consider this situation, particle in the ring. And this, by the way, is in my notes, so no need to copy it, really. All right, so particle in the ring. Like with all the constants, Hamiltonian will look like this. We put back h bar squared 2m r squared. And we have a second derivative with respect to phi, right? So this is pretty much a constant, and this is our second derivative. Now the function that we're looking for will be a function of phi, the angle, and it will be when the operator, which is this is our Hamiltonian for particle on ring, right, acts on the phi. It gives us energies and the function back, right? All right, now let's say this constant, we put it to the right, okay, and what we will get is second derivative with respect to angle is equal to, a constant will be 2mr squared E divided by h bar squared psi, right? And for simplicity, let's call this n squared. Okay? N squared can be any real number. Okay? Not necessarily integer. And we will have it with minus sign. Because we had the minus sign here, and minus h bar squared, right? Okay then. So with this, it's one variable, so we can actually write the full derivatives instead of partial. Phi squared minus n squared psi. Okay. So this is second order differential equation that is similar to particle in a box, right? So we can do essentially the same solution, which is exponents, right? Now, generally, the most general kind of solution would be psi equals to some constant I n phi plus b minus I n phi. Why is that? Oh, simply, if you just look at the differential equation, then you have second derivative plus n square function equals 0. Then the second derivative of the general solution is going to be I n squared, which is n with minus square, right? Plus b exponent of minus I n phi minus I n squared, which is also going to be minus n squared, right? So then minus n squared from here and from here can be taken, and the rest is just a function again, right? So second derivative will be minus n squared psi, and when you add it with n squared psi, you get 0, right? Now, this is all great, but we have a condition that, first of all, function integrated with its square over the angle, this must be 1. That's normalization condition. And the second, more important, is that we have a function on a circle. So that means, say, if we have angle phi, then function must be a single valued object, which means that psi at 0 should be equal to psi at 2 pi, right? Because 2 pi is the full circle. So say function changes somehow over this circle, but it must come back to the same value after 2 pi, and then it can go again in the circle and so on and so forth. But the idea is that this condition must be satisfied, or generally it doesn't need to be 0. 0 can be chosen anywhere. So that means the second condition really is psi of phi plus 2 pi is equal to psi of phi, right? That's the boundary conditions that we have. Instead of compare this to the particle in the box, where what we had as a boundary condition is that wave function at 0 or at the left boundary and then right boundary should be 0, right? And instead of that, we have a different boundary condition, and the functions must be like this. Okay? Now, it turns out that if you put these two boundary conditions, one boundary condition and normalization condition, then you will end up with what? With the condition that n must be essentially here phi plus 2 pi must be equal to n phi if we exponentiate that, right? So simply, if we substitute phi by phi plus 2 pi, it should be the same function as if we didn't substitute phi by 2 pi, but just keep it phi, right? So what helps is this exponent, and what this means, because we can just simply factorize the exponent of I n phi plus 2 pi is equal to I n phi exponent of I n 2 pi, right? And so then we need to have this equal to I n phi. Plus or minus doesn't matter, both terms. We can do this should be true for both components of psi. So what does this mean? It means that I n, or rather n2 pi, should be integer, right? Because the exponent of I n2 pi, according to the earlier expression, is cosine n2 pi to n pi plus I sine 2n pi, right? And for this to be 1, this should disappear. This should be 1. So what do we have? What's the condition for cosine to be 1? Well, n must be integer. Not half integer, but integer. Because cosine is here. And if we have, say, pi over 2, sorry, pi, instead of 2 pi, then we end up with minus, so minus doesn't really cut it, yeah? So because otherwise, you kind of start from some point, you come back, and then you end up with a function which is with a minus sign. You don't want that. You want exactly the same function, so you want to go in circles like this. And so n must be integer, and 2 pi will be multiplied by integer number. So what integer numbers do we know? Starting with 0, right? 0 plus minus 1 plus minus 2, and so on. Okay. Now. It turns out that it's kind of both of these parts, A and B, can be taken essentially independently, because n or plus or minus n, they are all in this interval, right? So really, it turns out that the situation is kind of a degenerate. So you can essentially take either these functions or those functions and mix them in with any a and b as long as they are normalized. Okay, because a and b, there are two constants, and normalization condition is one condition. Then out of a and b, you can essentially choose any a and b with the right ratio, ratio between a and b can be arbitrary. One of these constants is fixed by normalization. To make things simpler, you can just stick with these functions, right? And the only thing, we need to normalize them. Okay, so how do we normalize them? Well, that question pretty much everyone nailed on exam, so you guys know how to normalize things. And if you take this function, square it, absolute value, you're going to get what? This function, if you square it, what are you going to get? Absolute square. 1. And in the polar coordinate, we integrate between 0 and 2 pi, right? So this gives you the function, unnormalized function gives you 1. That means no integrand, you just integrate from 0 to pi, and then you get 2 pi. So that's your essentially n, and normalized function then will be 1 square root of n function, and this is 1 over square root of 2 pi psi, right? We could do the same thing, but with a and b. With a and b, we would get a squared plus b squared and some cross terms which will end up being, when we integrate them, they will end up into 0 because there are some exponents essentially, and the limit, integrating the exponents with limit 0 and 2 pi, we'll end up with exponents taken at 0 and subtracted the exponent at 2 pi, and so those are the same. So the cross terms will disappear, and the normalization condition would be a squared plus b squared 2 pi square root of that 1 over this thing, right? So that would be more complex normalization factor. It can be done as well. Well, we will stick with a simpler version. And you understand in a moment why, well, not maybe in this lecture, but or maybe in this one. You understand why the simple choice is is better, because there is important operator that we'll introduce, and these functions will be an eigenfunctions of those operators, while this mixed version is not an eigenfunction. It's kind of a momentum versus kinetic energy situation. Right now we're considering just kinetic energy, and that's why we can kind of combine those two exponents together. If we consider analog of momentum, which here will be angular momentum, they will have different angular momentum, eigen energies or eigen values, and so you should not really mix them together if you are concerned about angular momentum operator. Now, let's just finish the particle in the ring problem, and we found the functions. They should be 1 over square root of 2 pi exponent of I n phi, right? That's the functions, where n is integer. And what is left is to obtain what? So in any eigenvalue problem, you have eigenfunctions and values, right? So what are the eigenvalues? They are already, well, here, E's, right? So what are they? Well, since n, we just need to inverse this expression, n squared equal to 2mr squared e. We will enumerate them by n, right? And h squared with minus. So that means n squared h bar squared divided by 2mr squared. These are our energies. Like particle in a box, right? Here, the radius can be considered like a box, interestingly. Right? Although you would think that 2pr should be the circumference of... but, on the other hand, circumference of a ring is proportional to r, right? So it's not like an area of the circle, that's circle in circles, right? So circumference is proportional to r, so dimensionally this is like particle in the box problem where radius is the size of the box. Okay, and now if we draw the energy diagram, it's going to be with degeneracies, because n plus or minus, we can have n which is plus and minus integer numbers. In particle in the box we didn't have that. All n's were positive. But here we can have n's positive and negative. But those positive and negative will be exactly the same in energy. And say n equals 0. So energy for that will be 0. And then for n equals plus minus 1, this is n plus 1 and minus 1, we'll have, well, h bar squared 2mr squared, right? Then this one n plus minus 2, and so on and so forth. That's the diagram, which is very useful because I will explain today. You probably all heard of 4n plus 2 rule, right, in organic chemistry. So it turns out that this thing can explain 4n plus 2 rule. That's why it's so useful. Because after all these aromatic compounds, they're like a particle in a ring. Let's say benzene. You can think of benzene as a particle on a ring, because the pi system is like delocalized. They like to draw these resonance structures, right? And so essentially this is like equivalent to Kikule's structure. Okay, now how does 4n plus 2 rule come? Well, because of the structure like this, you can see that electrons are all paired up. We'll talk about spin at the last lecture, but you know that they all kind of paired up, and considering this as orbitals, right? So this is 2. Then the next layer will always contain, if you fill it, will contain 4, right? And the next one will contain 4, and the next one will contain 4. And so generally 4n plus 2 will be the structure, or like the number of electrons in the systems where every layer is filled up, right? And why is this good? Because you can see that well, there's pretty much, it goes by layers, right? And going to the next layer, or going like this, or not filling up the level, what it allows to do, the system, is that there's a degree of freedom, essentially there is a possibility for distorting the system, because let's say we have a situation like this, which is kind of anti-aromatic, right? So this would be octatetraene, right? Which is not aromatic, and more than that, there is a bond length alternation. So double bonds are shorter, single bonds are longer, right? So why is this thing distorted essentially? It is distorted because if all bonds are the same, then it's a nice planar structure, would be nice planar structure like a benzene, right? But it's distorted. Why is that? Because here we only consider electrons. In reality, there are nuclei, and nuclei can move and distort the structure. Now, here you need to believe me that, and it's proven, like Jan and Teller proved, and it's called Jan-Teller theorem. What they proved is that there is always a distortion in a highly symmetric system where there is a degeneracy between unoccupied and occupied orbitals. There is always a distortion that will bring this orbital up and this orbital down, right? So that kind of makes sense. If you can distort the system so that the empty orbital will go up in energy, but it's empty, so there is no energy price to pay for that. And if this orbital is occupied, and you can distort the system so that it goes down, you're actually winning in terms of stabilizing the system, right? So that's what happens when you don't fill the layer of essentially this layer of two orbitals that has 4 vacancies. Okay, so you always will have a distortion that can lower the energy, and that's what happens in octatetraene. Now that cannot happen in benzene, because any distortion that brings this orbital, say, down will bring this orbital up, so it's not really beneficial, and system stays like a particle on the ring, essentially, right? So this 4n+2 rule, stability of aromatic systems, and why they are 4n+2, not 4n+1 or 4n, it's because essentially that the energy structure comes all the way from the particle in the ring. Okay. Now, interestingly, actually there are some extensions of this rule. If you consider octatetraene not in a singlet state where things are paired up. Singlet that means like all electrons are paired, like the total spin is 0. But now if you say excite electrons and make them into triplet state, they have the same spin, right? Then it seems like, well, we have kind of the system with 4n electrons, and it shouldn't be aromatic, but in reality it is aromatic, because now again this electron cannot jump here and release this orbital, right? Why can it jump here? Because these two electrons, they have the same spin, and by Pauli repulsion they cannot, like by Pauli rule, they cannot be on the same orbital, right? So they occupy 2 orbitals and they kind of fill this layer, right? So there is again no distortion that can lower this and gain something, because this guy will go up, right? And the rules for the triplet is not 4n+2, rule will be modified to 4n, and people are talking about this as a big deal, but in reality, and publish papers on that, but in reality it's just a particle on the ring problem, and it's all very particle on the ring plus Pauli repulsion, and yeah, you can kind of understand why, if say you create a triplet state of octatetraene, it becomes aromatic. And you can even consider, by the same logic, bigger systems. It's better be in a circle rather than, say, naphthalene, anthracene. Those kind of things are trickier. They cannot be described just by simply particle on the ring, because the topology again is different. But aromatic compounds with one ring, they can pretty much describe by particle on the ring. model, right? You don't need to even go further into the structure. Okay? So that's the power of a simple model. Now, let's see how quantitatively we can describe, say, spectrum of benzene with this particle on a ring. Okay? So the trick here is to, I guess, put the right parameters, so the radius in this case. So in benzene, we have empty third layer, and if someone asks what's the spectrum of, like, what's the lowest excitation of benzene, that would be going from here, going there. So it's n equals plus minus 1 goes to n equals plus minus 2, right? So that's the excitation. All right, so then delta E will be E2 minus E1, where subscripts are n's essentially, and then we have h bar square to mr squared and so this is benzene, right? And if we all the carbon-carbon bonds are the same, and so the distance is 1.4 angstroms. And because the kind of triangle that we can build using the side of hexagon and the center, then it's equilateral triangle. So then the radius can also be taken as just a CC bond, right, in this case. So R is equal to 1.4 angstroms. And then delta E, in my notes, this is 3h, not bar, but just a normal Planck constant squared, 8 pi squared mass of electron r squared, right? And then if you want to calculate things in nanometers, then delta E is h nu, which is hc divided by lambda. And from that, you can calculate what lambda is. It's 8 pi squared cmr squared divided by 3h. And this is 213 nanometers. Okay? While experimental, this is kind of calculated from this simple model. Experimental lambda is 260 nanometers. Okay, so still in ultraviolet, so it's not bad for such a simple model. Okay. Any questions? You look puzzled. Right, so we ignore all that. And because of that ignorance, these numbers are different, and because of the other things that we ignored here. Right, so we also ignored all the non-pi electrons, like sigma electrons, right? So we ignored all that, and we considered in this problem that only pi electrons experience this kind of potential of a particle on a ring, while sigmas are more localized, right? They stay on their sides, All these ones are more delocalized, and that's why for them this model is more appropriate. Now in labs, when you do calculations, then the methods that you usually use, they are they treat all electrons. All right. But if you calculate benzene with any method of your choice, like Hartree-Fock probably, or Bifrelip, DFT, so then you can find this structure as well in the list of orbital energies. You can find the structure like that, which will describe 4n+2 rule. Okay, those will be valence electrons compared to the core electrons, which sit somewhere at the bottom. Okay. Any more questions? All right. So let me put the slides, because there's a lot to write, and I would rather just put them as some of these equations on the screen. All right, so we kind of finished this problem with particle on the ring, and the next topic would be describing particle on a sphere. But before we go there, there are certain operators I need to introduce, and one of the basic operator which will be very useful for us is angular momentum. Now, angular momentum, this L cross product of R and P, right, where laser pointer, where R is a position and P is the momentum, right? So in classical mechanics, this quantity is something that is conserved when particle moves on the circle, or essentially around the center. Okay, so if you don't have energy dissipation, then total energy, of course, is conserved. But also, if the forces in the system, they are central, so they depend only on the on the distance from some center, then angular momentum, this quantity, will always be conserved. And this vector product or cross product, this is again our old friend that can be written as determinant 3 by 3. These are our unit vectors, essentially instead of x, y, z, because x, y, z are they are related to the position, essentially variables. Here the Cartesian unit vectors are I, j, k, and then once you calculate, let's say, Lx is this minor, so this determinant of y times pz, and minus zpy, so those are the three components of the angular momentum, right? And this can be written like that in either for quantum or for classical mechanics, right? But now if you think about this for quantum mechanics, because position and momentum, they generally do not commute, right? Px doesn't commute with x, and py, for example, doesn't commute with y. It turns out that in quantum mechanics, Lx, Ly, Lz, they don't commute, okay? And there are profound consequences of that. which is what is the first consequence of 2 or 3 operators not commuting with each other. Yeah. They cannot have the same eigenvalues? No, that's not quite right. Actually, eigenvalues can be changed by adding a constant operator, right? So you can play with the eigenvalues relatively easily, because imagine, yeah. So it's not eigenvalues. It's what is the starting point of for measurement process? It's eigenfunctions, right? So when 2 operators don't commute, you cannot find the common set of eigenfunctions. And that means, in terms of measurement, what does it mean? The most, the most famous principle of quantum mechanics, that quantum mechanics is a fuzzy science where things are uncertain, cannot be measured. What are the 2 quantities that everyone remembers that you cannot measure? They, by the way, on this slide. Seriously, only 1 or 2 people? The most famous quantities in quantum mechanics that cannot be measured together. Position and momentum, yes. R and P, right? Why can't they be measured? They don't commute. That means they cannot have eigenfunctions. Why do we need to have the same eigenfunctions to be measured? 2 operators. Why do they need to have 2? Oh, it's the same eigenfunctions to be measured at the same time. Well, eigenvalues can be different.
You only look at the distribution on the other one, even if one is an eigenfunction.
So what does it mean we can measure? Let's get to the basics, because I keep saying that. I can say this all day long. Do you really understand? It's like, okay, so how do you understand the statement? This can be measured with certainty, if I want to be precise. You see, I've been talking about this a whole semester. Only 2 people know. So what are you guys, aren't you wondering when something like that passes by? Yeah. What does it mean?
It means that we have an eigenvalue of an operator, of a measurable operator that is specific to an eigenfunction.
I'm a bit confused. What are you saying? So what does it mean if we say that this quantity can be measured with certainty?
It means that an operator, a particular operator, a measurable operator, has a specific eigenvalue on eigenfunction.
But it's always the case. Give me an operator which doesn't have that. Every operator has an eigenfunction and eigenvalues. And eigenfunctions can be paired with eigenvalues. Right? So this is a basic relation. Any operator A have eigenfunctions, eigenvalues. Yet, sometimes we say the particular quantity can be measured with certainty, and sometimes we say, oh, position and momentum cannot be measured at the same time. Yeah.
If you set up an experiment under a certain condition, if you repeat that experiment, you will always get the same result.
Yeah, that's kind of a practical aspect of what I said. Can you now translate it to the theoretical? Like we're doing theory here, right? We don't do experiment, but it's nice to know what does it mean in terms of experiment, right? But in terms of theory, we have a system with a function psi, right? And say we have an operator that corresponds to some property that we're interested in measuring. So what you said, if I make 1,000 or millions of copies of my system, I measure my property of interest, I'll get the same result every time. not a distribution, the same result. That's what experimentally it means we can measure things with certainty, right? Because if we do the same experiment on the same system and get the different result, that cannot be said as something that measured with certainty, because every time you do it, it's different, right? So there's no certainty, right? That's what we call uncertainty, because we do the same experiment on the same system and get different results. Come on, this is very disturbing, right? It's like, I don't know, you pack your fridge with food, you go in the morning for a breakfast, you open it, it's a different stuff. You close it, you open again, it's different stuff, right? So what will you think? That you got, mental disease or something of some kind, right? So you'll call 911, or you'll be really disturbed if something like that happens. But that happens every time if you choose the wrong variables or choose the wrong observables and the wrong wave functions, right? So in quantum mechanics it happens all the time, because a psi is not equal to lambda psi. So the operator or the property you're measuring, if your function of the system is not an eigenfunction, then you get the distribution, right? So you can measure the same system over and over and you get different results every time. That's uncertainty. Now, how is that related to being able to measure two quantities at the same time? If we have A and B, two quantities, then if those two operators corresponding to the quantities, if they commute, then it's possible to find a wave function that is an eigenfunction for both of them, though eigenvalue can be completely different. That is not important what eigenvalues are. What is important is that the function is an eigenfunction for both. And that means you prepare, doesn't matter how many copies, and you start measuring A, B, A, B, A, B, and you get exactly the same results for A all the time, and for B, different results, but consistently the same, right? So this B's. So now if A and B do not commute like X and P, that means you can make your function an eigenfunction for one, but it's not going to be eigenfunction for another, right? So that means even if you get the consistency for one, you won't get the consistency for another. That's what we cannot measure them together. Now, how is that related to angular momentum? It's kind of interesting. It's even more disturbing in a sense. In classical mechanics, all these xp's and l's, all the components of angular momentum, they all can be measured at the same time with a kind of very good precision. But in quantum mechanics, because this Lx doesn't commute with Ly due to the operators that comprise them, right? And Ly doesn't commute with Lz, and essentially all of them don't commute with each other, then you cannot measure all three components of angular momentum. You can only measure one of them at a time, in the sense that you can prepare a function, the function of the system, which will be an eigenfunction of one, but not two others. So there is a uncertainty in the components of angular momentum. Okay, and that is an important thing to remember. That's another kind of important operator, where x and p, they are different operators. So you may say, okay, so what? I cannot measure x and p. But here, it's the same operator. It's just two different components of the same operator, but they also cannot be measured at the same time. Okay? So that's the kind of the importance of this. Now, the another quantity that we will be looking at is the square of or the length, essentially. But the operator which we'll be looking at is the sum of the squares, L squared, right? And because those are three components, then the L square is just the sum of the squares, okay? It turns out, I will just announce the result. It turns out that this is some kind of magical operator from the point of view of algebra. And there is a such science as the Lie algebras, right? So in the science of Lie algebras, these operators are called Casimir operators. So what is special about them, in any algebra there could be Casimir operators. These are operators which commute with all elements of algebra. And here elements of algebra are L, X, Ly, and Lz. So the magic quality of L square is that it can commute with Lx, Ly, and Lz. Okay? So what does this mean for us, for people who study quantum mechanics, is that L square and one of these guys, they can share eigenfunctions. Okay? And we will be using, and in the hydrogen atom, you probably remember there is this SPDF, right? So those guys, say, let's take P electrons, right? There are 3 of them, Px, Py, Pz, and then there is S, and there is 5 Ds. So it turns out that these P's and S and Ds, they're just different eigenfunctions of L square. Okay? Px, Py, Pz, these 3 components, are different eigenfunctions of Lz. Okay? So Lz will separate those guys. L square doesn't separate those guys. Okay? So, but still, because L square and Lz, they commute, you can always choose eigenfunctions for both of them. And these are eigenfunctions that you learn in general chemistry, S, P, D, F, and so on. There are also eigenfunctions that are coming when we consider what are the eigenfunctions of L square are and Lz. Okay? So that is the kind of the significance of L square and L. Well, to say the truth, whether you choose X, Y, Z really doesn't matter. You just need to choose one of them. Okay? So because they all commute with L square. And now here is some algebra that, or some geometry that you probably have seen before. It's a right-hand rule where for the cross product, where in order, since the L is a cross product, then R and P, they are oriented like this, and the L then looks up. If they are oriented like that, then L looks down. So this will not be very important for us. Now, what is the significant part? So the significant part here is that for any isolated particle, right, if we fix the distance from the center, then the kinetic energy actually turns out to be in 3-dimensional space as L squared divided by 2mr squared, right? So this is different than what we saw for 2-dimensional case, but it's only slightly different, because for the 2-dimensional case, we had this d squared d phi, and it's not, of course, L squared. But what we will see in maybe even in this lecture, that this second derivative with respect to angle, it's actually just Lz squared. Okay, just in the polar coordinates. Okay. And then we can essentially look at the eigenvalues of Hamiltonian in terms of eigenvalues of L square, and this is the importance of this expression for that matter, because once you found the L square eigenfunctions, then they will be automatically eigenfunctions of the kinetic energy. Yes.
You said it's LZ squared?
Yes.
Is that significant, or could it be LX squared or LY squared?
No, the kind of the labeling of axis is somewhat arbitrary, right? I call it LZ because the plane that we were considering is actually XY plane, right? And the circle was in XY plane. So now if your particle kind of classically moves within the XY plane, well then the only other component that is left is Z component. And the cross product, according to the right-hand rule, if X and P are here, then the Z goes perpendicular, right? So it goes outside of the plane of the board, right? And that's LZ. But generally, if you have three-dimensional case, and that's the particle on the sphere, in the three-dimensional case with a fixed distance, we'll see that the kinetic energy is not just the one component squared, but it will be all three components squared. Okay. Now, these are quantum mechanical expressions which you can derive easily yourself once you, you just put the, okay, where do they come from? You just saw that angular momentum was presented as a determinant, right? L is a determinant, I, J, K, then X, Y, Z, Px, Py, Pz, and then it has Lx, Ly, Lz components. Lx correspond to I multiplied by this, right? Ipz minus Zpy, and then you turn p's into operators, right? And those are your components. Very straightforward process in Cartesian coordinates. And then L square is just a sum of them. Now, it's not so straightforward when you go to the polar or spherical coordinates, but I'll just provide you expression. What is relatively straightforward is to see, once you write down what Lx and Ly are, that their commutator is very simple actually. That's why, it's partially why all these problems of particle on a sphere or particle on a ring or kind of hydrogen atom, why are they solvable? Exactly because they are written, their Hamiltonians can be written as some functions of angular momentum operators. And angular momentum operators, although they don't commute, it seems like that poses the problem. But the commutation relation, look at this. X and Y, when you consider commutator, it gives you Z. And then you can kind of rotate this relation circular, and you can kind of shift Lx to the second position, Lz to the first, and Y to the equal sign. Yeah, it's right here. So you can obtain two others expression by just circular substitution. But the main point of this is really, if you commute all three pairs, they only produce the other one, right? So X and Y by commuting produce Lz, Y and Z produce X, and Zx produce Y, right? So they don't produce anything else. They kind of, although they don't commute, but when you consider commutators, they only produce themselves, not other operators, because things could get, crazy, right, in general. If you take two arbitrary operators, then they will produce, say, third operator when you commute them. Then you take that third operator, consider the commutator with the first one, and it can produce the fourth operator, fifth, sixth, and so on and so forth. Like, it could be a never-ending story. Now, what makes these problems exactly solvable is that the commutator, they kind of create the algebra, which is closed, in a sense that when you consider the operation between two operators as a commutator, then it produces only the elements of the same algebra, which is Lx, Ly, Lz. So you don't go outside of that set. Okay. So that makes things simpler. All right. So now, as I was telling you, that this all can be just confirmed if you do the algebra, and it's end up being the commutators of X with say, px, and commutator of y with py. So if you do all that, you can obtain all these relations, and that will be one of the homework problems. Now, what also you can confirm is that Lx and L square, for that you can just use these relations, because L square is breakable to the Lx square plus Ly square plus Lz square, and it commutes with all of them. Okay, so it can share eigenfunctions with all of them. And this is essentially physical interpretation, or what I was telling you before, that since only L square is commuting with all operators, this is a very typical diagram people like to draw, is that, okay, you have an operator, right, and it's presented as a vector. In reality, what you can think of this as vector, usually physical vector, consists of numbers, right? And how do you get numbers? What do they show here? So this vector L is not really operator, it's the average of the operator with a wave function. Okay? So what they show here is that Lz value can be well determined. Say if you take a wave function which is an eigenfunction of Lz, then you know Lz for sure. You can measure Lz once, twice, 3 times. It always will be the same, right? So it's well determined, no uncertainty. The length of the vector comes from L square, and that commutes with Lz. So it's also the wave function that we consider. It's also going to be kind of certain for the length, right? So length is certain. Now x and y, what about them? They don't commute with Lz. What does that mean? They cannot be determined with certainty, right? And that's what this circle means. Essentially, if you measure Lx and Ly, so this is this direction and that direction, so the circle has a plane, xy plane, and that means when you measure x, essentially you can end up anywhere on this circle, right? But the length is fixed and the height is fixed. But where on this circle, you cannot determine. Now, z can be changed to x or y, and you can make the same consideration where you substitute z to x or y. Then if you substitute z for x, what will be certain is x component and length again, but z and y components will be uncertain. Okay, so that's the consequence of the fact that only component and L square commute, and components do not commute with itself, within themselves. Okay. And spherical polar coordinates. Here, the expressions which are not as simple looking as x, y, z, like Cartesian components. Like if you write this Lx, Ly, and Lz in a Cartesian form, then they are much simpler. Now Lz though looks quite nice. It's just a derivative with respect to phi, and we saw that in the particle on the ring. Now when we consider particle on the sphere, then we'll need to also consider Lx and Ly. These terms, they can be derived using the essentially definition of what polar coordinates are. No, in this case, spherical coordinates are, right? And chain rule again, right? So, because we know it's easy to write down what Lx is in terms of derivative with respect to x and y and z, right? And then you kind of move along and substitute all derivatives. And this is L square. This seems like not very simple looking expression, and that's what this is appendix with, you can look at all these lectures. So for today I'll finish here, and we will consider particle on a sphere next lecture. Now I posted all the lectures that we will be going over for the till the end of the semester on the Blackboard, so you can read up front, because there's a lot of material. I'll go, there is a lot of lengthy math essentially, right? And so I'll try to emphasize the physical aspect and what is this all about, but it's probably better for you to review before coming to the lecture, so that you can actually see some insights in what I'm saying, rather than be bogged down into the details that are not essential, right? And also I posted the exams previous year and the year before on the Blackboard, so take a look. So the final exam will be somewhat similar. I don't have PDF of solutions, but as I put there, the solutions will be communicated during the office hours, which will be April 3rd. Okay, so April 3rd, there will be last office, not office hours, tutorial session by TA. If you have questions on the problems for these exams that I posted, so please come by and she will be able to answer them, okay? And also don't forget to fill the evaluations for this course, right? So as I said, if we go over 95% limit in the response rate, I'll provide 2% bump in the final for everyone, okay? All right, thank you everyone.